Hi, everyone. Today we have Dootika Vats, who actually organized this seminar before me, so she's native to the seminar. She will talk about the new BFFs in MCMC, Barker and Bernoulli. Please go ahead.
Thanks, Yuri, and thank you for the invitation. Like I was saying before, I mean, it's really nice to be back speaking. I do not miss the sandwiches, though. I think I can say that with a great amount of confidence. Okay, so I'm going to be talking about the new BFFs in MCMC, which are Barker and Bernoulli. Of course, this is really a setup to get more people to come into the talk. They're not actually best friends forever, but we will be, interconnecting the contributions of Barker and Bernoulli and seeing how it contributes to Markov chain Monte Carlo. Okay, it looks like I can't really see anybody or see a text or chat box. So if you have a question, please feel free to interrupt me at any point, and I'll figure out a way to get back to the screen if I need to. All right. So the first slide is going to be the typical sort of Bayesian paradigm to introduce you to the notations I'm going to be using. So we're considering a Bayesian model for a parameter of interest theta. I have a prior distribution of on theta, and having observed some data, I'm going to update my likelihood to obtain my posterior distribution, which, as people in the audience will be mostly familiar with, the posterior distribution is typically not available to us in complete. We often only know it up to a unnormalized function pi tilde, which we can't really integrate to obtain what the normalizing constant is. So the posterior is often complicated enough and often only known up to pi tilde, which is its unnormalized form. I'm only presenting sort of a Bayesian paradigm because it's natural in this case, but a lot of what we're going to talk about can be constructed in general for intractable sort of target distributions. So most people in the audience here would know that this is a great scenario because it means bread and butter for people here, because we can actually implement Markov chain Monte Carlo algorithms to be able to sample from this posterior distribution and still be relevant in the 21st century. Right, and so that's the main goal of implementing MCMC algorithms, to learn something about this posterior distribution. Sort of a generic MCMC sampler or setup for this could go as follows: that given a certain value of the parameter theta k at time point k, I want to generate theta star in the first step from a proposal kernel Q, and I generate theta star from that. And then I will accept this value theta star with probability alpha, and we'll talk about alpha later on. Or with probability 1 minus alpha, I will reject this value. In that, I will set the next step to be the previous step. Okay? And so in many different MCMC algorithms can be basically written up in this sort of accept reject framework. And of course, in this, we've really not used the posterior distribution evidently anywhere, but it is expected to be encoded in alpha. So alpha needs to be chosen in order to satisfy invariance so that we actually eventually do get samples from our target distribution of interest. And so alpha is going to have pi in it somewhere in some form. Okay? And of course, if alpha can be evaluated, and that will, I'm foreshadowing a little bit of what's coming because I'm saying if it can be evaluated, then obtaining an event with probability alpha can be done if we draw a uniform 0-1 draw, and checking whether this draw is less than equal to alpha, because that's an alpha probability event. So if alpha can be evaluated, then I can basically combine this algorithm with sort of this step in step 2. Okay. And go ahead and run this accept reject based MCMC algorithm. Okay, but and so a common acceptance function alpha that's typically employed is the popular Metropolis Hastings acceptance function, which is this alpha MH, which I'll denote by alpha MH, is the minimum of 1 and the ratio of the target densities at the 2 contested points times the ratio of the proposal density at the 2 contested points as well, just the inverse of that. Now, one of the reasons the Metropolis Hastings acceptance function is so popular and so commonly used and so easy to implement is because unknown normalizing constants are easily canceled out because they occur in both the numerator and the denominator, so that we can write this in the form of pi tilde and pi tilde only. Right? So if pi tilde is in fact known to us, then MH can be implemented easily. And again, there is foreshadowing here because I'm saying if it is known. So now I want to talk about the cases when pi tilde is not known, or pi is cannot really be evaluated. And so the situations when that might happen is when we want to consider target distributions that cannot be evaluated, in the sense that they may, for example, be in the form of an integral that cannot be simplified. Right? So this is not all the cases that we're looking at, but just for a motivation, consider pi theta y to be an integral of g theta eta given y d eta, where eta, the integral with respect to eta, is not solvable. So in this particular case, if we want to evaluate the acceptance ratio from Metropolis Hastings, we'll not be able to do that because we may be able to evaluate G, but of course we won't then be able to evaluate the integral over here. And so problems like this can arise in problems with priors and constrained spaces, which is a particular example that we're going to look at in this talk. They'll also occur potentially in missing data problems, where in the likelihood we're trying to impute values, so there's natural expectations that arise in there. And very naturally, they occur in Bayesian inference for diffusions, which is a significant area of application for our work, but I'm not going to talk about that application here. Right, and so as I've said before, alpha MH, in this particular case, even though if there are normalizing constants that may cancel, that's fine, but pi still will be in the form of an integral. Right, and so this will not be, we won't be able to evaluate this. So in this particular case, there are other options available to us. Of course, there's pseudo-marginal MCMC algorithms. There's approximate methods like the double Metropolis Hastings, and there's a few others out there. And all of these have their pros and cons. In the interest of time, I'm not going to talk about comparisons. I'm happy to take questions about that later. But I'm just going to focus on what we are going to look at instead. And in comes in our first protagonist, which is Barker. So instead of the alpha MH acceptance probability in a generic accept reject based MCMC algorithm, we can use alpha B, which is the Barker's acceptance function, which is this popular or reasonably well-known form here, instead of the alpha MH, right? This is naturally alpha B, the acceptance here is naturally less than alpha MH, and that's one of the reasons that it's not as popular as Metropolis Hastings. And that's because there is an ordering on the acceptance rates, there is a natural ordering in the asymptotic variances as a consequence of Peskin's ordering result, which I'll take a quick detour to just explain a little bit. Okay, so although Barker came up with this acceptance function, one of the reasons it's not employed is if I look at an ergodic average like this coming from the Barker's kernel or the Metropolis Hastings kernel, then the asymptotic variance of the ergodic average from the Metropolis Hastings kernel is always less than or equal to the asymptotic variance of the ergodic average from the Barker's kernel, which implies that Metropolis Hastings is always going to be, more efficient than Barker. So there may not be any reason to use Barker's if Metropolis Hastings can be implemented. But on the plus side, the variance from Barker's algorithm is not going to be insanely large because it is bounded above by 2 times the asymptotic variance of ergodic averages plus a little bit more of the target variance of h under pi, where h is some L2 function. All right. So although Barker's is more inefficient, it is not too much so. So if we do want to look at Barker's as an alternative to MH, it's not the worst idea in the world, basically. But of course, Barker still doesn't solve our problem because even in the Barker's acceptance function, we have pi coming in everywhere, right? We have, and if pi cannot be evaluated, then we can't really evaluate the Barker's acceptance function. And this is where to the rescue comes the second protagonist, which is Bernoulli via the Bernoulli factories, okay? So first of all, what is a Bernoulli factory? I'm going to give a simple introduction, but keep our focus on what we are using a Bernoulli factory for. So a Bernoulli factory is an algorithm that generates a Bernoulli event of probability h of p for some function h using Bernoulli p events. So you can think of this being some sort of a factory where you give it a bunch of Bernoulli p events and out comes a Bernoulli hp event. Okay, and that HP event comes without the need of possibly even evaluating H. All right. But for our problem, what we want to do is we want to be able to construct a Bernoulli factory that can get us events of probability alpha B, the Barker's acceptance probability, without evaluating it. And the reason we want to do that in the accept reject, in the AR step 2, which says, set theta k plus 1 to be equal to the proposed value theta star with probability alpha b. If we want to do this and we don't want to evaluate alpha b, but we just can get an event with probability alpha b, then I can just set theta k plus 1 equal to theta star when that Bernoulli event is 1. Bernoulli random variable returns 1. Okay? And so instead of drawing a uniform random variable and comparing it to an evaluated form of alpha b, I can just generate a Bernoulli event with probability alpha b. Okay, so this is what we're going to try and do. So in this paper, what was proposed was the following technique. Was if we can find, and this is the if, but if we can find C theta such that pi theta given y times q theta star given theta is less than equal to C theta. Okay, that's the first thing we need. We need to be able to upper bound this product. So from here on, because I'm going to say this product a few times, I'm just going to call this pi times q. Okay, so if we can bound pi times q by some C theta, where this is not a universal bound for all theta, it is a local bound for a given value of theta, then what I'm going to do is I want to be able to set this pi times q as C theta times P theta, where I want this P theta to be in 0, 1. Okay, I want it to be a probability. So the way I do this is I just set P theta to be pi times q divided by C theta. All right. And this sort of construction maneuvering is just so I can write this, I can make this sort of decomposition. Okay. Now, what we are going to do is we're now going to be able to construct a Bernoulli factory that produces an output 1 with probability this over here, which is the alpha B acceptance probability. And this is going to be done via the 2-coin algorithm. All right, so I'm going to explain the 2-coin algorithm in the next slide. All right. So no prizes for guessing how many coins are involved in this 2-coin algorithm. It is indeed 2, depending on the situation we are in. So the first step of the algorithm is you draw a coin C1 from this Bernoulli distribution, a Bernoulli random variable with this probability of success. If C1 is 1, then you draw C2 with Bernoulli P theta star. If C2 is 1, then you output 1, and output 1 here means that go ahead and accept that proposed value. And if C2 is 0, then you go back to step 1 being this particular step here. Okay. Now, if the original C1 is 0, then you draw C2 from Bernoulli P theta. If C2 is 1, then you output 0, as in you reject the proposed value and you set the next value to be the previous value in the context of the Markov chain. And if C2 is 0, then you go back to step 1, which is again this step over here. Okay. And it can be fairly reasonably shown that the above algorithm outputs 1 with probability alpha b, the Barker's acceptance probability. Okay. So if we can implement this 2-coin algorithm, we will not need to evaluate alpha b in order to generate events of with probability alpha b. The only sticky part here is these two steps, step 2.1 and 3.1, which says we want to generate coins with probability of success P star, but I know P theta is nothing but pi q divided by C theta, and I know I can't evaluate this pi. Okay? But there are many situations where actually that can be done reasonably, and I'll just show you an example of how, just to put your mind at ease. is in order to sample from Bernoulli, to obtain a sample from Bernoulli p theta, let's look at the construction we had before, the type of construction we had before, where pi was of this form over here, integral of g with respect to eta. Now, just for the purpose of demonstration or example, just assume, if we assume that we are in a situation where eta is bounded, then we can draw n uniform within that support and set m sub theta to be this particular realization, or this particular function q times g at the drawn value n divided by c theta. And we can then easily show that expectation of m theta is p theta. Now, if I then generate a coin C2 with Bernoulli m theta, of course, this is conditional on n, then the marginal probability that C2 is equal to 1 is exactly p theta. So C2 marginally is a Bernoulli p theta coin. Okay, so in fact, if we can do this particular construction over here, or something similar to this, as long as I have an unbiased estimate of p theta, I can actually go in and produce Bernoulli p theta coins. But the thing to remember over here is I don't need multiple draws of uniform over here. Just one is fine, because I'm not trying to get a good estimate of p theta. I'm just trying to get a random variable which is unbiased for p theta, right? So just generating one coin is fine, or one uniform draw is fine. Okay. Right. So now, hopefully, if your mind is put at ease, then I can go back to the algorithm. But now I notice that in steps 2.3 and 3.3, the algorithm asks us to go back to step 1, as in the algorithm asks us to restart. So what I mean here by restart is that as soon as, if p theta or p theta star are small, then I go to 2.3 and 3.3 often. And as soon as I go to this point often, I go back to step 1 and then continue this process over and over again. Okay. And what happens is, for certain proposals that are proposed values that are far away in regions of low probability, particularly, p theta and p theta star are often small, which means that for values far away, often this gets stuck in quite very, very long loops. And you'll see in the example how long of loops we're talking about here. And it makes really implementing this in a wide variety of examples quite difficult. It pretty much can only work when you have very, very tight bounds that you've created, and you're using really, really small step-sized proposals. And again, we'll see that in the examples. And so what we wanted to do was think about what else could we do in this case with a seemingly nice and elegant sort of method over here, but sort of also make it work. And that's where we get the idea that what really worked for MH and Barker's was the fact that the acceptance probability was a ratio of the density pi at the two evaluated points, pi theta star and pi theta, which was great because if the normalizing constants were unknown, those go away. And that's one of the reasons that implementing this was so easy, either in MH or Barker's. But now this particular feature, that the acceptance probability is a function of this ratio, is no longer useful to us because we can still not evaluate this. So we can now allow ourselves for problems like this to go outside the class of acceptance probabilities that look like the ratio of the density at the two contested points. And when we open ourselves to that, we find that at least we can find one Bernoulli factory algorithm that really does help us quite a fair bit. And so I'll go on to that phase later, but let's look at what the Portkey-Barker's algorithm is. So we propose the Portkey-Barker's algorithm, where the Portkey-Barker's algorithm looks very similar to the regular Barker's algorithm, except there's this little bit of d theta comma theta star that's added to the denominator. Now, this d theta theta star is some function of theta and theta star. And what we need is for this alpha p, the first thing is to yield pi invariant so that we're still targeting the right density. And if d theta theta star is symmetric, this is in fact a necessary and sufficient condition. then alpha p yields a pi invariant Markov chain. So if I choose this function d so that it is symmetric, then I can still run a pi invariant algorithm using my accept reject based MCMC. However, it is fairly reasonable to see, as long as because this d is greater than 0, that this is less than or equal to alpha b, the Barker's acceptance function. And because of that, sorry, for some reason I can't write in the margins here. But because of that ordering, it also yields that we are not going to be as statistically efficient as the Barker's algorithm, the original Barker's without this term d. And in fact, so I'll get to that in a second. But what the specific form, though, that we consider of d is this particular form over here, where again, the rest of the terms are the Barker's acceptance terms, but then d is chosen to be 1 minus beta divided by beta, c theta star plus c theta, where beta is greater than 0, and c are the upper bounds that were obtained on pi and q. Okay. So for this, because we don't want to lose out on efficiency, statistical efficiency, we ideally want to choose beta to be really close to 1 or fairly close to 1 in this particular example, so that we get back Barker's algorithm. Because if you set beta to be equal to 1, then this just turns out to be 0, right? So beta equals 1 gives us back the regular Barker's algorithm. And because we know we're not going to be as efficient, we'd like to be able to get some bounds. So we do get some bounds on the variance in the efficiency. They're not the best, and it's very difficult to get very specific bounds, but we do have the following: that for beta greater than 0, the limiting variance of ergodic averages from the Barker's algorithm is less than equal to beta times the variance from the Portkey algorithm, plus a little bit of residual from the target distribution. And so if beta is set to be 1, we actually give ourselves a little bit more room for them to have reasonable equal variance, but of course we can't really say anything because of the inequality here. In the other direction, we can also say something, again, not terribly satisfactory, but we can say something. So if there exists gamma greater than 0, such that both p theta star and p theta are bounded away from gamma, then the variance of the Portkey Barker's algorithm with beta is less than equal to the Barker's algorithm plus a term that decreases if gamma is large. Okay? So if your p theta and p theta star are reasonably large, then there's going to be less loss in efficiency. But if they're small, you're going to start losing out on efficiency. So all of this seems to be negative, in the sense that then why use Portkey Barker's at all, right? And the reason is it brings a level of robustness into the Bernoulli, the corresponding Bernoulli factory, that really makes this practically extremely useful. So let's actually take a look at the equivalent Portkey two-coin algorithm, and you'll understand, if you're a Potterhead, as to why this is called the Portkey algorithm. So what you do is, first step is you draw S, a Bernoulli draw with probability of success beta. If this is 0, then immediately you reject. Okay, so if S turns out to be 0, then immediately you reject the proposed draw, and set theta k plus 1 to be equal to theta k. However, if S is 1, then you do essentially the same exact two-coin algorithm as before, except when the algorithms loop, they loop at step 1, which makes you draw another Bernoulli algorithm that lets you escape out of really long loops by going to the Portkey. Okay, and this particular setup, what really helps over here is that if you choose beta to be close to 1, then you're often going to be in here. In this part, S's turn is often going to be 1, in which case you're going to be running the regular two-coin algorithm. But even if you run beta to be equal to 0.99, then approximately 1 out of every 100 draws, you have the opportunity to escape out of what would have been otherwise been a really long loop. Okay, And that really brings this robustness into in the implementation, because as you'll see again in the example, in implementing the first 2-point algorithm, sometimes you'd just be staring at a white screen, not knowing when the computer will tell you we've finally done one accept reject step. Okay. The one thing that's going to be relevant for the example is you can actually do this whole Portkey setup by getting a lower bound on your target distribution as well. So if we define, if we divide our acceptance ratio, acceptance function by this product over here, the product of pi and q at theta star and the product of pi and q at theta, and then I divide it in the Portkey step. So I get essentially something that looks very similar, except I get the inverses in the numerator and the denominators. And then I get a different d function that also still remains symmetric. So you get d prime. But for the Bernoulli factory, this takes still a very similar form of a divided by a plus b plus c, which is the form that we want for the Bernoulli factory. Again, my corners aren't working. Okay. So it takes the same form. And so I'm not going to tell you the exact flipped Portkey algorithm, 2-coin algorithm for there. But if we can lower bound pi q, that means we now have an upper bound for pi inverse and q inverse. We can implement a similar Portkey 2-coin algorithm for this flipped Portkey. Okay. And this really, the flipped one is what's going to be useful in the example that I'm going to show you. All right, so this might be many things in the air. So let's actually go to an example. The application is going to be the application of a Bayesian correlation estimation model. So suppose we have data y1 up to yn. That given the correlation matrix, our IID normal 0 R, where R is a P by P correlation matrix. Okay. And our goal is to be able to get some understanding of what R is for the data observed. So, which means I'm going to have to set priors on R. So this is going to be a little tricky because R is a correlation matrix. So first I define SP plus to be the set of P by P correlation matrices. And so Lighty in 2009 and co-authors set the following priors, where here for the prior for R, they said each element of R, Rij, is going to get a normal prior mu sigma squared, except there's going to be the restriction that altogether the whole matrix needs to be a correlation matrix, a P by P correlation matrix. So they're not truly, of course, they're not truly independent because they're restricted in the form that they all have to form a correlation matrix. And so if you look at this restriction, the normalizing constant over here needs to be accounted for, and that is L inverse of mu comma sigma square is the integral that R is in SP plus of the PDF upstairs, right? So if I choose not to put priors on mu and sigma squared and just put priors on R, then I don't have to worry about anything because this is just a constant, right? This L just becomes a constant. But in any reasonable Bayesian setup over here, I would want to put priors on mu and sigma squared. And so when I do put priors on mu and sigma squared, L mu sigma squared is no longer a constant. It's a function of mu and sigma squared. And so I can now see the intractability in my target distribution. My target distribution downstairs has a function that's in the form of an integral. Okay, so I put some standard priors, or at least they put some standard priors, normal 0 tau square for mu and inverse gamma for sigma squared, and interest is in the posterior distribution. Okay. So what does the MCMC steps for this posterior distribution look like? So to implement MCMC, we're going to use a component-wise algorithm where we're going to update R component-wise, and then mu, and then sigma squared. So we have full conditional densities of R available to us, and that in the sense of up to proportionality, and that does not have any intractable integrals as part of it. So we can just use a regular Metropolis Hastings update with some Gaussian proposal over here to generate samples from to implement this particular conditional step. But for mu and sigma squared, we're out of luck a little bit, because over here we have the conditional density of mu given R and sigma squared proportional to a function the function L times the remainder product. And this L is the problem because we can't evaluate this. Right? And so Lighty et al. 2009, they use this approximate inference shadow prior approach that augments a different prior into the model that sort of changes the original model and then approximates a posterior distribution that is an approximation to this approximation as well. And they get something that's reasonable. But over here, we're able to do exact inference by being able to implement these Portkey and regular Barker's Bernoulli factory-based algorithms. Okay, so let's see how that might work. So what are the details of that? So we'll be doing a flipped Portkey setup, where I'm just going to focus on the mu update. So for mu, recall in the previous slide, I had the conditional density in front of you, where L, again, recall, was such that its inverse took the form of this integral. Now, this is why the flipped Portkey is natural here, because the inverse is in the form of an integral. And if I can upper bound the inverse, then I can upper bound this integral. And I can also easily generate unbiased coins from this integral. Unbiased coins, not from this integral, but unbiased coins that estimate this integral. Right? So obtaining an unbiased estimate of L inverse is simple. We are in a restricted space. I can use importance sampling using truncated normal proposals. And I can also quite easily obtain a bound on L inverse, again, using the fact that the correlation matrix, each component is between -1 and 1. And so I get, using a truncated normal argument, I get the following upper bound on L inverse mu sigma squared. Now, because I've been able to upper bound L inverse, I now have a lower bound on F, because this part of the density is fine. I don't have to worry about this part of the density. Okay, so here we can use the flipped Portkey Barker's algorithm and go ahead. So what we're going to do is we're going to do regular MH steps for each Rij. Then we're going to do flipped Portkey for mu. Then we're going to do a flipped Portkey for sigma squared as well. Okay, and the first set of plots I'm going to show you is going to be a run something. I run this Markov chain for 100,000, a length of 100,000. And I jumped a little bit because I do have to tell you what data set we used. Is we studied the correlation of the closing prices of 4 major European stocks, 91 to 98. I will not be able to name these stocks. My knowledge in finance is as low as anyone else's. All right. So what I show you on the x-axis are the iteration time. And on the y-axis are log of the number of loops for mu. So recall for each update of the mu, I used a flipped Portkey. And I can use flipped Portkey with beta equals 1, which is nothing but Barker's. And beta equals 9, which is a Portkey, which about once every 10 iterates, it gives you the opportunity to escape. And on the y, I stress again, the y is the log of the number of loops for mu. So what you see is that there are enough instances where for Barker's, the number of loops required is greater than e to the 10 for the same given proposal. So these are the same given proposed values, right? And so that means that we have these long wait times to just observe whether this value is going to be accepted. This particular iteration is going to be accepted or rejected. And we have to wait for the Bernoulli factory loops to do e to the 12 loops. And that's a pretty large wait time for just one run. But more painfully, it's really scattered. Sometimes it can do things very quickly, as you can see here, but there's odd times, and in some runs it can take more than an hour to finish maybe one update. And that the lack of knowledge of how long a particular simulation will take is really what gets very annoying in trying to implement the original 2-coin algorithm. But of course, naturally, the question should be that, okay, you can do these fast sort of times for the Bernoulli factory, but do you get anything reasonable? And if you look at the correlation, the ACF plot for mu and sigma square, they show, there's a little bit of visible difference, but statistically speaking, they're probably very similar to each other. So there doesn't seem to be a lot of loss in efficiency, at least as viewed through the ACF plots, but we can do some other reasonable comparisons. So what I do now is I run the Markov chain for length 10,000 but I repeat the simulation 10 different times. And I calculate the effective sample size using Barker equals 1 and Barker equals 0.90. And the ESS is fairly comparable. These are estimated ESSs, so they have their own variability. I also report the ESS per second, and this is where we do certainly see improvement. Now, it's not astronomical improvement, but we see some improvement, certainly. If I'm just going to jump down to this line over here, what I also note in my simulation is what is the maximum number of loops that was required for a full sweep of 10,000 steps. And the average estimate of the maximum number of loops required was about 2 million for the original Barkers, and it was about 34 for the Portkey Barkers. And this is really the impact of the difference of just staring at a blank screen for 10 to 15 minutes to days versus immediately knowing that, okay, that value was not great. It had to be rejected to begin with. Okay. Now, the thing though is we did 10 replications because really my patients only allowed me to do 10 replications because beta equals 1, which was the original Barker setup, would get stuck in these large loops and I would get angsty and wouldn't know whether it's going to take 5 days or it's going to cut back to me in 5 minutes. The other thing is what we did was for both flipped Portkey for both mu and sigma squared, we used optimal, or close to, I should say, optimal proposals coming from Metropolis Hastings. So we almost, tried to get about, 20, again, these margins, about 23% acceptances. But the problem with that is we couldn't really get down to 23% acceptances because in trying to get towards it, we really had to increase our variance. And when we tried to increase the variance, the original Barker's 2-point algorithm would get extremely annoyed. And in me forcing it to go do these larger jumps and give me wait times that were exorbitant. But I want to go back to this question of optimal proposals or almost optimal proposals, because I'm not really using Metropolis Hastings, right? And so if I do in this problem, it's a realistic problem where somebody else actually interested in estimating a correlation through this Bayesian paradigm would want to do this, would want to run an efficient algorithm, but wouldn't know how to tune their algorithm because this is Barker's and not MH. And we don't know optimal scaling results for Barker's acceptance functions, right? And so almost all of the literature that we've seen and read is based on the acceptance functions being Metropolis Hastings. So the question is, can we use the same rules as we use for Metropolis Hastings to scale Barkers? So I'm going to go into a little bit of a different work that was heavily motivated by this first work and come back to this again. Okay, so I'm going to do a little bit of a detour. And the detour is going to be optimal scaling beyond Metropolis. And I'm going to talk about how we'd want to do optimal, or how could we particularly, how have we done the optimal scaling in general, outside of just assuming the acceptance function to be Metropolis Hastings. Before I continue, the work was led by a master's student, Sanket Agarwal, who's, I think, attending also and will be attending Warwick as a PhD student, I believe, whenever travel is possible. So yeah, it'd be nice probably to have him there and maybe ask him and bug him if you want more details on this. Okay, so the setup here is going to be the Roberts et al. Seminal work setup. If you are unfamiliar with the work in this area, then I'm going to disappoint you because I'm really not going to go into a lot of details. It is just meant to be the quickest advertisement, and that's about it. So I apologize beforehand. So here's the whole chunk of the setup. So we consider target distributions that are of the form that they're decomposable. Each marginal distribution is essentially the same, they're independent, and D denotes the dimension of the distribution of the vector. My class of densities is a reasonably well-defined class, and as usual, as it's common, and as was done in the first paper, we're assuming that the expectation of the 8th moment of the derivative of the log is finite, and the fourth moment of the double derivative of the log is finite. And I will denote by J the second moment, the second moment of the derivative of the log of my univariate density function f. Okay, so this is the general sort of assumption bracket of the general setup of the paper. And then my proposal is going to be a Gaussian proposal with variance sigma squared sub d, where for some L, sigma squared d is going to be L squared by d, essentially. So as dimension increases, I want to linearly reduce the variance, and this is going to be the scaling that's going to work for the class of acceptances. I say the class of acceptances because what we're going to do here is we're generating a proposal, and then we will choose to accept or reject the proposal based on certain acceptance probability. And instead of fixing that probability to be MH, we set it up to be as general as we could make it. So we set alpha to be the acceptance function so that there exists a balancing function G such that alpha x comma y is G of the ratio of pi y by pi x. So for example, for alpha MH, G of Z is equal to minimum of 1 comma Z. And for example, for Barker's, G of Z is equal to Z pi 1 plus Z. Of course, it may be evident to you that by this setup over here, I am leaving Portkey out of this. So sadly, Portkey is not going to be part of this optimal scaling literature. Okay. So this is for practicality and for essentially the proof to also work, because if it doesn't satisfy this, it becomes really difficult to get the proof to sort of go along. The second, quite critically, we need invariance so that we're targeting the right density. So G should satisfy this equation where G of Z is Z times G of Z inverse. And we need an additional sort of relatively weak assumption, which is required in the proof, that G of e to the Z should be Lipschitz continuous. And most acceptance functions we've looked at have been able to satisfy this. Okay, then, so the Roberts et al. Paper, and since then many others prove weak convergence and obtain optimal scaling for alpha equals alpha MH. And so what we're just going to do is extend their proof to the general class of acceptances and look at what we get in terms of the results. Again, I apologize, I'm not going to be able to explain the general proof paradigm of this because that's not really the point, but Sanket will be there and you can bug him in the future. So we speed up the process by a factor of b. And so this is the process sped up by a factor of b. And we just look at the first component, the one-dimensional process that is just the first component. Okay. So this UD, this process UD, weakly converges to U. We show this where U satisfies the Langevin stochastic differential equation as displayed below. Right. This H alpha is the speed measure over here, and it is dependent on alpha. So it's dependent on the acceptance probability that you've employed. And H alpha is L squared M alpha, where M alpha L is the average acceptance rate for this setup. Okay. So M alpha L turns out to be the integral of G of e to the b with respect to a normal random, where b is a normal random variable satisfying this mean and variance as indicated by this PDF. So up until here, things may look familiar to you. What's really different is the form of the average acceptance rate, because that's where alpha comes in. And so in previous proofs, alpha was set to be alpha MH, and then M alpha was obtained in closed form, where I use closed form to mean it was obtained in a probit function form. So what we do in the proof is we basically keep the integral intact and don't even try to solve it. We do reach a point where it becomes a little bit difficult, but then we're able to use a few clever tricks using invariance of the acceptance function to basically get a reasonably straightforward result that retains exact weak convergence and gives us this particular average acceptance rate. So typically what we want to do after this is to say, well, this is the average acceptance rate, M, and H of alpha L is the speed measure, and tells you for different values of L, you fix alpha, and tells you for different values of L, how quickly is the process converging to its limit. And you'd want to maximize this so that you get the best possible convergence. So when we maximize HL, we get some L star, and that's going to be my optimal proposal variance. And the corresponding M alpha L star is going to be the acceptance rate to tune to. Okay, so the magic numbers that come about for Barker's turns out to be asymptotically 15.8 acceptance rates as compared to 23.4 from Metropolis Hastings. And the optimal proposal variance is L square by D, L square star by D, where L star is 2.46 compared to 2.38 for M edge. So what we learn is that if we are going to be using Barker's acceptance functions, then actually our optimal proposal variance should be larger than what we would have used for Metropolis Hastings. So the fact that we're rejecting less because of using Barker's implies that we want, when we do accept, we want the opportunity to accept farther jumps. And that's why that's why intuitively the optimal acceptance, the optimal L star is larger than it would be for M edge. Okay. And additionally, if we look at the plot for average acceptance rate on the x-axis and efficiency, which is H, the corresponding H of L, we plot the curve for this for both M edge and Barker's. And what we see is that the decline in efficiency as acceptance rate increases is slightly more steeper for Barker's than it is for Metropolis Hastings, indicating that if you go and accept more than you want to, more than the 15.8, then the decrease in efficiency is more, which means that if you choose smaller proposal variances, which will yield larger acceptances, your efficiency is going to drop more than it would have for M edge. So actually in Barker's, we want to be able to use larger proposal variances even more than in M edge. And so this particular point is exactly what I want to take back, and this particular comparison to our previous example and our implementation in the Barker's and Portkey Barker setup, because what we want is to be able to tune properly. And we weren't able to tune properly before if we were using the regular Barker's two-coin algorithm. So I give you the first two lines from the table again, which was 10 average replications, just to see where the numbers were at before. And what I do is I now tune the proposal to approximately 15.8 acceptance. And when beta is 0.90, I'm able to draw 10,000 samples in 40 seconds with an estimated ESS to be 514. Okay, and then the estimated ESS is just to tell you that it didn't just, it's not that it just gave me all 0 acceptances. It did reasonably well. And this is Portkey. But if I do the regular two-coin algorithm, then for the regular two-coin algorithm, we waited 24 hours and we're not able to get 1,000 samples, and the simulation I had to possibly stop. It's possible I got only 2 samples. I was just not wise enough to put a marker for after every step when the sample was successfully obtained. So really, the problem is not only that the original two-coin algorithm is slow and gets stuck in loops. You can't really implement it as efficiently as you'd want to begin with. Okay, I'm clearly have gotten a little bit over time, so I'm going to try and wrap up. So this is the main reference for the first part of the talk, which was the Bernoulli factory MCMC for intractable posteriors, recently accepted to Biometrica. The advantages of this over some of the other competitors is, the one thing is the Markovian dynamics are mildly altered when you set beta to be close to 1, and it is an exact MCMC algorithm, significantly more robust than the original two-coin. Now, of course, it's not as efficient as MH, and yes, doing this, universally in a black box style is going to be very difficult. You do need to find, good bounds for your problem, for it to work reasonably well, and that's something we're well aware of. The second part of the talk was work led by Sanket, and then Chris and Gareth were part of the project as well, and then in the previous as well, Chris and Gareth and Flavio. So very much a Warwick sort of effort here. Where this is optimal scaling for MCMC beyond Metropolis. The results in here have lazy MH and other acceptances. And it's just that the setup and the proof technique can be very easily used to extend optimal scaling results in the future and the past to other sort of assumptions and other techniques and other proposal distributions. So we sort of encourage everyone to say, so keep their results as general as possible. No need to really fix alpha equals alpha MH unless you need to. That's about it. I'm happy to take questions, and I hope I'm not offline and you've been able to listen to me for the past hour.